All right, good morning. It's probably might not be morning for you. It's morning for me. There you go. We're going to talk about conservation momentum here. You ready? I hope so. I don't know. I'm talking to you like you're sitting in front of me. Okay, here we go. Law of conservation momentum. Hopefully you remember this from honors physics last year. What we learned last year was this, that in the absence of external forces, the total momentum of a system will always remain constant. The way we wrote that last year was this. We said that the total momentum of a system before your objects interact has to equal the total momentum of the objects after your objects interact, assuming there are no external forces. So, system, just a couple quick review things. A system, collection of objects in a problem. Usually it's two cars that are running into each other or whatever. All right. External force. An external force is a force which is applied by an object that is not in the system. So if you've got two cars that are colliding, your system is the two cars, cool. But as soon as you add in friction or air resistance or something, that now becomes an external force. All right. That said, usually collisions occur in such a small amount of time that even external forces don't make that significant of a difference. Okay. Let's see. So, and then we're going to talk about two sort of types of problems. There are collisions. This is a situation in which two or more objects are moving and they run into each other. And then this is something I did not make this distinction last year as well as I should have. An explosion is a situation where the two objects interact, and when they leave the interaction, they have more energy than they began with. Okay. So, like if you picture a bomb, right now the momentum is 0, right? Okay, and then it explodes, and now you've got more energy, right? Where did the energy come from? Well, there was chemical potential energy in the gunpowder, and that chemical potential energy got converted to kinetic energy, right? So we gained energy, right? Last year we did a problem where Santa was sledding, and he ran into a bear. And so at the beginning of the problem, here's Santa, here's the bear. So the idea was at the beginning they both had the same amount of velocity, and then Santa was like, whoa, freaky, bear. And so Santa pushed the bear, and as a result, he slowed down. But in this interaction, you actually gain energy. And the reason is because Santa's converting the chemical potential energy from his Cocoa Puffs or whatever Santa eats for breakfast. He's converting that into kinetic energy. Okay, so those are examples of explosions. All right, the idea is usually you've got. Well, I guess that's not true. Okay, so there you go. All right, now this last sentence is a little bit out of context here. It says this is all a result of Newton's third law. So what do I mean when I say this is all? I mean, this is all a result of Newton's third law. All right, let's think about why. All right, so suppose we've got two objects that interact in some fashion. Maybe they're running into each other, maybe they're exploding apart, we don't know. Here's object A, object B. Okay, but just by nature of the fact that they are interacting with each other, they're exerting forces on one another. All right, so here's the force of object A pushing object B, here's the force of object B pushing object A, right? They have to do that. That's Newton's third law, okay? And then the idea is, because there are no external forces, this is it. This is my whole drawing, right? So if I want to find the change in momentum on object A, well, that's equal to net force times time, assuming the force is constant. Oh, well, that's just the force of B times the time, right? And similarly, the change in momentum for B is the net force on it times the time, which is the force of A times time. All right? Well, what's the relationship between these two forces? They're equal and opposite, right? So that means that this is just negative FB times T, right? Oh, so that means the changes in momentum for my two objects are equal but opposite, right? So whatever momentum is gained by object B has to be lost by object A. And as a result, all you're doing is you're transferring momentum from one object to the other, but you have not changed the total. So the total amount of momentum the objects have before the collision or interaction is equal to the total amount of momentum they have after the interaction. This is true always. Okay, for every collision, that is true. Your total momentum does not change. All right, and it turns out there are, a few different types of collisions. All right, so we learned this last year. All right, so completely inelastic collision is a collision where the objects stick together. All right, so the idea is all of your objects are going to have the same final velocity. All right, and it turns out that this is a situation which maximizes the loss of energy. All right. So where does the energy go? Well, it gets converted to heat. Some of it goes into deforming the objects, right? If you picture two cars colliding, when they collide, the cars get bent up, and that takes energy to bend metal, right? And when it bends, it converts to heat because you're breaking molecular bonds and chemistry, right? Okay. All right. An elastic collision is a collision where the objects don't stick together and all of the energy is conserved. So an elastic collision is a collision in which total kinetic energy before the collision is equal to the total kinetic energy after the collision. Okay? All right, and then if you have a collision which is neither completely inelastic nor elastic, then it is simply called inelastic. Okay? So you kind of do it by trial and error. When I do this, I usually check first, do they stick together? If so, it's completely inelastic. Thing two, if it's not completely inelastic, then you check to see if it's elastic. Okay? If it's elastic, that just means that your total kinetic energy is the same before and after. And if not, then process of elimination tells us it must be inelastic. All right? Now, what if it's an explosion? Well, we already talked about that, right? An explosion is an interaction where the objects gain kinetic energy. So this would be a situation in which your total kinetic energy before your collision is less than the total kinetic energy after your collision. Okay? As opposed to this guy, in which case your total kinetic energy initial is greater than your total kinetic energy final. Okay? All right. So, do you know what? Actually, I guess after you've eliminated options 1 or 2, then you got to see if it's 3 or 4, right? Because sometimes it won't be obvious that it's an explosion. Okay? And I guess this statement here doesn't really say why you gain the kinetic energy. And the idea is it's got to be converted from some other sort of potential energy, either chemical potential energy in like an actual explosion, or maybe you've got a spring, and when the two objects interact, the spring decompresses and pushes the objects apart, right? Okay, so let's run through a few examples here, all right? So this first example is basically going to be kind of a review of what we did last year, okay? But we're going to build on it, all right? So even though this is a review, you should probably watch it, okay? So when I do these problems, I always make a drawing. So we got a 1,250 kilogram truck rolling at 5 meters a second, and then it collides head on with a 750 kilogram car rolling at 8 meters a second. So here's our truck. It's got a mass of 1,250 kilograms. It is going to collide. All right, so sorry, I had to pause there. Let's see. So where were we at? We had our truck, 1,250 kilograms. It is rolling at 5 meters a second. So the velocity of the truck initially 5 meters a second. Let's see. It's going to collide with a car. Car. The mass of the car is 750 kilograms. The velocity of the car initially is negative. Notice it tells us that it is a head-on collision. So it's going at 8 meters a second. Immediately after the collision, the car is going backward. But notice, backwards for the car is this way. And we are looking for the final velocity of the truck and determine what kind of collision it is. Velocity of truck final is something. All right, so that is our setup. So let's do one of these, and we'll do this. So To solve it, remember, the whole premise is that our total momentum before the collision has to equal the total momentum after the collision. So that means that the momentum of the truck before the collision plus the momentum of the car before the collision has to equal the momentum of the truck after the collision plus the momentum of the car after the collision. So mass of truck times velocity of truck initially plus mass of car, velocity of car initially equals mass of truck, velocity of truck final plus mass of car, velocity of car final. All right, so that is all conservation of momentum. All right, and then you plug in your numbers. It's plug and chug. I'm not gonna go through the math. But so if you solve this, you end up getting looks like -4 meters per second. Okay. All right, so that is that. So now let's determine what type of collision it is. So to do that, let's go back to here. Oops, too far. So let's see, is it completely inelastic? Well, that would only be true if the two velocities were the same, right? And they're not. So it is not completely inelastic. So now we need to see if it is elastic. So to do that, the question is, does our total kinetic energy before the collision equal our total kinetic energy after the collision? All right. So sometimes there are little shortcuts you can take. So the shortcut we can take here is this. I'm noticing that both cars slow down, right? The truck went from a velocity of 5 to a velocity of 4, and the car went from a velocity of 8 to a velocity of 7. Both cars slowed down. That means both cars lost kinetic energy. So we must have lost some kinetic energy, so it's got to be inelastic. All right. But if you didn't notice that, here's how you would do the calculation. What you'd have to do is you'd have to say, all right, well, my total kinetic energy before the collision is the kinetic energy of the truck before the collision plus the kinetic energy of the car before the collision. So that's 1/2 the mass of the truck times the velocity of the truck initially squared. And then 1/2 mass times velocity of car initial squared. And plug in numbers and get a number. Okay. So if you do that, oh, I didn't figure it out. Okay, whatever. But you can plug in your numbers, right? You're going to get some number. Okay. And then repeat the same process, but for final, right? So it's the kinetic energy of the truck final plus the kinetic energy of the car final. So that's 1/2 the mass of the truck times the velocity of the truck final squared plus 1/2 the mass of the car times the velocity of the car final squared. Okay? And plug in your numbers, and you'll get a number that's smaller than your initial kinetic energy was. All right? And so that tells us that it was an inelastic collision. All right? If both cars had sped up, or in some other fashion we had gained kinetic energy, maybe one of them slows down, but the other one super speeds up, you gain kinetic energy, then we call this an explosion, right? Maybe the car was a Pinto and the gas tank exploded when it got hit, and that added energy to the collision. Okay. All right. So this hopefully was review from last year. All right. Now, example 2. So this time the problem tells us that it's oops. Whoa, what happened? So man, sorry. All right. Example 2. Same exact starting information. The difference is this time it tells us it's a completely inelastic collision, which means that they're going to stick together. All right? So how does the math work here? Well, it's the same drawing we had before. In fact, I am going to... You ready? We've got... oh, no. It's going to let me? Maybe? Fingers crossed. Yes. Copy. Paste. Hey-ya! Neat. All right, so there we go. So there's our starting information. And this time they stick. So the idea now is the velocity of the truck final, I don't know what it is. The velocity of the car final, I don't know what it is, but I do know they're equal. So let's just call it VF. Okay? So then to solve, you use that same big equation. So it's the mass of the truck times the initial velocity of the truck plus the mass of the car times the initial velocity of the car equals the mass of the truck plus the mass of the car times the final velocity of the car, and solve it, right? So, let's see. guess we can figure this out. So this is, what, negative 6,000 is this. So, and over here, we're going to get 6,250, I think. Is that right? 5,000, yeah. Equals, over here, you've got 2,000 VF. So you're going to get 250, oops, 250, sorry, equals 2,000 VF. So divide both sides by 2,000, and your VF turns out to be 0.125 meters a second. All right, and that is completely inelastic. I should comment, I'm terrible about this. Most people say perfectly inelastic. It's really what I should say. Somewhere along my education, I started saying completely inelastic. Perfectly inelastic is probably more widely accepted. So, all right, let's see. All right, now, elastic collisions. So what if this was elastic? That last one was perfectly or completely inelastic. What if it was elastic? Well, it turns out that elastic collisions have a very special property. All right? So we're going to do some algebra to find that special property. All right? So here's the thing. For whatever reason, I've never seen this property in a book. Okay? So like on the AP test, if you ever have to use this property, you should derive it. Okay? But it's easy to derive. Okay, so check it out. So because of conservation of momentum, suppose we've got two objects that are colliding, and the problem tells us that it is elastic. And we've got our two objects are objects A and B. All right? So conservation of momentum tells us that the change in momentum for object A is equal but opposite to the change in momentum for object B. So that means the mass of object A times the velocity of A final minus the velocity of A initial is equal to the opposite of the change in momentum for object B. So that's the mass of B times, and I'm just going to switch, instead of doing VF minus VI, I'm going to do VI minus VF to, to get that negative sign in. Okay? All right, so that is a thing that we know. All right? So here is equation number 1. I know that those two quantities are equal. All right, now, the other thing that's true is this. Since the problem tells us that it's elastic, we know one other piece of information. Specifically, we know that the total kinetic energy before the collision must equal the total kinetic energy after the collision. But since there's only two objects, that means that one of the objects is going to gain gain energy, the other is going to lose. So we can also write this. The change in kinetic energy for object A is equal but opposite to the change in kinetic energy for B, right? Because any energy lost by one has to be gained by the other. Okay, so change in kinetic energy. Change in kinetic energy. So that's 1/2 mvf squared minus 1/2 mvi squared, right? That's change in kinetic energy. You can factor out the 1/2 m. And then you get VF squared minus VI squared. All right, so check it out. Let's see what happens here. So our change in kinetic energy for object A, that's going to be 1/2 times the mass of A times the VAF squared minus VI AI squared equals, same thing, but for B, and again, to get this negative, I'm just going to swap my initial and final. So that equals 1/2 the mass of B times BF squared. Nope. We're going to swap our signs, right? Oh my gosh. Let's try this one last time. Okay. So where are we going to go from there? Well, I happen to notice a couple things. First of all, the 1/2s cancel out. Secondly, this is a difference of squares. So this becomes MA times, let's see, difference of squares. So that's VAF minus VAI times VAF plus VAI, right? And similarly, this guy is a difference of squares. So that equals the mass of v times the velocity of v initial minus the velocity of v final times the velocity of v initial plus the velocity of v final. Cool. So everything below this green line is because the collision is elastic. All right, but now, so check this out. Look, this, let's call that, I don't know, let's give it a name. How about Q? All right. All right. Oh, well, that means that this is Q. Oh, but that's equal to this. This is Q also. This is Q also. Aha! And so what we have discovered then is that this equals this. We've just discovered that for an elastic collision, the following statement is true. VAF plus VAI equals VVF plus VVI. All right, now conceptually, these numbers have no meaning, right? Like there's not really any sense in adding an initial and a final velocity. But in terms of problem solving, this is super, super powerful, okay? So anytime you have an elastic collision, automatically we know that this statement is true. All right, if you ever use this on an AP test, then you've got to be able to derive it, okay? So you should be able to derive this, okay? That's a thing. It is a thing I can put on a test if I so chose. So you should know that, all right? So let's use it. Here we go. Oh, so this, I always see this in books. I don't know why. Further algebra shows you that if the initial velocity of one of your objects is 0, then you get this. I don't think you need that at all for my class. I just left the slide in here because it's in a lot of books. To me, that is not nearly as useful as this guy down here. Okay? So here's our example. So we're going back to our truck and our car. They're having that head-on collision. This time the collision is elastic. So here we go. So there's our drawing once again. All right, and this time the collision is elastic. So this time we have two unknowns. We are trying to find, we are trying to find the velocity of the truck final, and we are trying to find the velocity of the car final. All right, but because the collision is elastic, that buys us something. All right, so I would usually start with that fact. Since the collision is elastic, I know that the velocity of the truck initial plus the velocity of the truck final equals the velocity of the car initial plus the velocity of the car final. So that means that, you know what, let's do this. Well, I guess it doesn't matter, whatever. Okay, so here we go. So this means that 5 plus VTF equals -8 plus VCF. So let's add 8 to both sides. So that means that VCF is VTF plus 13. All right, there's equation number 1. Notice, two unknowns, we're going to need two equations. Here's our first one. Okay? So for our other equation, we're going to use our total momentum initial equals our total momentum final. So the mass of the truck times the velocity of the truck initially plus the mass of the car, velocity of the car initially equals the mass of the truck, velocity of the truck final plus the mass of the car, velocity of the car final. Let's plug in our numbers. Let's see, 1250 times the velocity of the truck initially is 5 plus the mass of the car, 750. Velocity of the car initially is -8 equals the mass of the truck is 1250 times the velocity of the truck final plus the mass of the car times the velocity of the car final. But look, there's the velocity of the car final. Cool. So now we've got one equation with one unknown, which we can solve for, okay? All right, I am not going to go through the math because I believe that you guys can do that. If you do that in this particular problem, you get, oh, I didn't solve it on my notes either. All right, let's pause it. All right, so if you go through the math, simplify, you get this. Move your variables to one side, simplify, you get that. And here's the final velocity of the truck, negative 4.75. And then this will allow us to find the final velocity of the car, which is going to be negative 4.75 plus 13, which is 8.25. All right, and then you can check and make sure that your kinetic energy is the same before and after. And you will be pleased to discover that it does. All right, so that is that. All right, the last thing is, I guess we got to talk really quickly about a couple special types of collisions. So these are just some things that you should know. So first of all, so these are all going to be problems in which object B has an initial velocity of 0. So it turns out if object A is moving to the right and it collides with object B as at rest, and both objects have the same mass, then what will happen is object A will stop and object B will keep moving with the same exact velocity that A had before the collision. Okay, so here, this V is equal to this V. This is like a simple billiards problem, right? The idea is you've got two balls. Right, so this guy is, moving along. Oh, seriously? There we go. So this guy's moving along, boom, into this guy. This one stops, and the other one keeps moving along at the same velocity. Okay? All right. Special case number 2. It turns out if object A is way bigger than object B, then what happens is, and this is a little bit involved. If anybody wants to see the proof, I can show you. But it turns out because this object is so massive, its change in velocity is insignificant. But as this mass gets closer and closer to infinity, what happens is when it collides with the smaller object, object B, which is at rest, it slows down, basically 0. Okay. And object B will acquire a velocity that is twice as big as the initial velocity of object A. Okay? I don't know that I've ever used this one, but it's worth knowing. All right, the next one is very important. It's the opposite. Okay, so here we've got a little object colliding with another object that is colossal. All right? So if the collision is elastic, what will happen is the object will bounce back at the exact same velocity it had going in. Okay? So this is like a tennis ball bouncing off the earth, right? If the collision is perfectly elastic, it will bounce up from the earth at the exact same velocity it had when it hit the earth, okay? Because the earth's mass is so big that its change in velocity is virtually 0, okay? So in other words, object A retains all of the kinetic energy. All right, and then the fourth one we'll deal with a little bit more in the next video. It's called a glancing collision, okay? Notice this time when object A hits object B, it's not a straight-on collision, right? And so what happens is object A is going to bounce off this way, and object B is going to bounce off this way. And it turns out that after the collision, assuming the two objects have the same mass, the velocity that A travels at will be perpendicular to the velocity that B travels at, okay? Useful thing to know when you play pool, too. All right, but this only works if the masses are equal, okay? I think that's all I got for you. Yep, all right, cool.